All right. So let's approach this in a very systematic fashion, and we'll start with 2 electron groups on the central atom. And what we'll do is increase that to 3, and then 4, and 5, and finally 6. And we'll look at the different combinations of bond pairs and lone pairs that can constitute 3, 4, 5, excuse me, and 6 electron groups on the central atom. We're going to make use of representative formulations here instead of actual molecule examples, because I think those are best left to you, but you'll see that every example that you try will actually fit into one of these categories that we're going to do. So we will exhaust all possibilities here and maybe practice drawing these exemplar molecules with you, and then you need to try them and do them on your own, okay, for best results. So we'll start off very straightforwardly with 2 electron groups on the central atom, and I think we know intuitively that this is going to end up a linear geometry, but nonetheless, let's carry on. So if I have 2 electron groups, and again, your textbook is calling them groups, they're really pairs, but if I have 2 electron pairs or groups on the central atom, I only have one possible distribution of those 2, and both of these are going to be bond pairs, so I don't have any lone pairs at all. If I represent my central atom as A and my bond pairs as X, or the atoms that I'm bonding to, then I have AX2. And with no lone pairs, I write E for lone pairs, but it's E0. And we may not even include the E0 at all. You may just see this as AX2. Now, is this a formulation that you need to be able to write? No, I'll answer right away, because you'll be asked for specific molecules, specific examples. We are using this, your book does, to categorize all the different molecules and central atoms in particular, that will have the resulting geometry. Okay, so what I will do then is I'll end up with a Lewis structure that has 2 electron pairs on it, and I have a Lewis structure that has 2 electron pairs on the central atom, and I have to arrange those that minimize the mutual repulsion. And so I know that, so let me just draw that Lewis structure that I would be looking at. So that's the Lewis structure. And I would need to consider VSEPR approach on that Lewis structure. So I would see 2 bond pairs. How can they get as far away from each other as possible in 3D space? Well, in fact, they just do use a bond angle that is linear. And so the result is, I'll put it down here, that I have 2 single bonds. I'm sure that there are lone pairs around here that complete the octet, but the focus in this video is just on the geometry around the central atom. And so that's why the number of bond pairs on the central atom is 2. The number of lone pairs on the central atom is 0. This is my geometry, and it is 180 degrees bond angle. Now there are 2 geometries that we need to know. The electron group geometry, and I should have made that a title, but I will write it out. The electron group geometry is how, or I should say indicates how these bond pairs and lone pairs or total electron groups are arranged. And so in this case, the electron group geometry is linear. The other geometry that we need to know is the actual shape of the molecule. And so that's called the molecular geometry. And I'm abbreviating it here, GEOM. The molecular geometry, what is the shape of the molecule? It's also linear. And as we go along, you'll discover that when there are no lone pairs, then the number of pairs are the bonding pairs, and so the electron group geometry is the same as the molecular geometry. But soon I'll have lone pairs here to consider in another molecule, and I'll discover that the way the electron groups are arranged, their geometry is not necessarily that of the molecule, because if I have a lone pair, it's not bonded to another atom. So we'll see those as they come up. But this exhausts all possibilities for 2 electron groups on the central atom. So the next one we'll do or consider is 3. And let's just turn this around and carry on. So with 3 electron groups on the central atom A, let's first consider that all 3 are bonding and none are lone pair, in which case the formulation would be AX3 and, if you like, E0. So my Lewis structure is going to have a central atom with 3. And perhaps my Lewis structure with bonds was looking something like this. And I know that I may have drawn it with right angles, but Lewis structures don't tell me anything about the geometry. So now I want to use this as my first step in a VSEPR approach to find out what that geometry must be. So now I redraw that central atom and I think for a moment, how can 3 electron groups arrange themselves in space so that they are minimizing electron-electron repulsions? And the way that they do that is they actually stay in the plane of the paper as I've drawn it here and arrange themselves in what's called a trigonal planar arrangement. And so again, I have 3 electron groups, and so my electron group geometry is trigonal planar. It's a trigonal planar geometry. The molecular geometry, what is the shape of this molecule? The molecular geometry is also trigonal planar. And again, I'm seeing that when I don't have lone pairs, when the total number of groups is the same as the bond pairs, then the way that the groups arrange is actually the way that the atoms arrange because I have no lone pairs. So trigonal planar, trigonal planar. And if you like, you can indicate that the bond angle is 120 degrees. You might see this drawn, and do our best attempt here at drawing a trigonal plane coming out of the paper, and I would draw the case of it. Now, your central atom is literally in the center of it, and my bond lines are like so. And so this is 120, this is 120, and this is 120. So this is a planar molecule. And most likely, if these are not hydrogens, they have a complete octet. But again, my focus for the moment is on the geometry surrounding the central atom. Whether I draw these in or not right now is not having an effect on that. The next thing that we'll try is, staying with the 3 electron groups, we'll make 2 bonding and 1 lone pair. Let's get a fresh sheet of paper for that formulation and carry on. So I said it's a systematic approach that we're taking here because we're doing these in order. So a total of 3 groups, 2 of which are bonding but 1 lone pair. So a central atom with 2 bonding and 1 lone pair. AX2E, or if you like, AX2E1. My Lewis structure would look like, at least around the central atom, it would have 2 bonds and a lone pair. So it would look like that. And the question is, what is the geometry? So I'll draw my central atom, and I consider, again, what is the arrangement in 3D space that allows these three, not just two, but three electron pairs to minimize their electron pair repulsion. Again, think of the acronym VSEPR, valence shell electron pair repulsion. And I'm back with three groups, trigonal planar. And so I'll put my lone pair here and my bonding pair at a kind of a 120 idea here and the other one here. So there's my two bonding pairs. And to emphasize that this is non-bonding, I put this little hood around it so it's not neatly pulled between two nuclei, but only attracted to one and then rather loose up here. It has the effect of maybe pushing down on this and making this bond angle either 120, and I'm just going to say about 120, because in some cases, especially where these are hydrogens, it could actually force them a little less than 120, a little closer together. So we'll just say about 120, because it's not perfectly 120 unless I have three atoms here, and if those atoms are the same. So here I finally have the chance to show you what happens when one of the pairs is non-bonding. And so my electron group geometry is 1, 2, 3 trigonal planar. So when it's 3, it's trigonal planar. But what is the shape of the molecule? The molecular geometry is not trigonal planar. And the reason it's not is because my molecule just extends from here to here to here, the atoms, and I don't consider the lone pair. And so my molecular geometry is what's called a V shape, or simply bent, and we'll go with bent. So again, the electron group geometry, 1, 2, 3, therefore trigonal planar. But because one is a lone pair, my molecule is really just bent. Okay, let's look up here for a moment. Can I have 3 pairs total with only one bonding and 2 lone pairs? The answer is no, not in our considerations. So we are actually done the category that has 3 total electron groups on the central atom. So what we're going to move to now is 4. And we're going to start off with the basic one, where all 4 are bonding, no lone pairs, and so my formulation is AX4E0, or simply AX4. So the Lewis structure that I would have that looks like this would have a central atom and then have 4 things stuck to it with no lone pairs. And if this were something like methane and those were hydrogens, they'd be fine with 2 electrons. But most likely, I have an octet complete. I'm just not putting in the 2, 4, 6, and total 8 electrons on each of these satellite atoms, because again, my focus is just here showing you these representative diagrams. Alright, so that would be my Lewis structure. So what is the geometry? Consider my central atom. Sometimes when we draw these, we actually make it look more like an atom, put a circle around it, especially where we have this geometry base of 4. Because the way that 4 electron pairs can arrange themselves in 3-dimensional space in order to minimize their repulsion is to do something like this. I'm going to put 1 up here, and then it sits on sort of a tripod, the rest of it, 1 towards the back, 1 towards the front, and 1 out this side. It's kind of like a little spaceship sitting there. But the important thing to remember is that all of these bond angles are the same. We'll get to that in a second. So this is how, and I make this a little shorter because I'm trying to indicate that it's going to the back here, pointing to the back, front side and back side, and then straight up. So the electron group geometry, in this case, is called a tetrahedral. It's a tetrahedral geometry. You don't immediately see the four sides there, perhaps, and you don't have to draw it this way, but I just want to show you that, in fact, it is a tetrahedral or four-sided. And the way that I do it is, see how the base is kind of a tripod? The base has a triangle base, and then there's a position on top. So I just do this, and that's how I draw my tetrahedral. And I can imagine spinning this around and it would look the same on each side, and I could actually flip it over and it would still look the same. So all four sides, there's one on the back, there's one here, there's one here, and there's one on the bottom, are identical looking triangular surfaces. And so the A is in the center, and we have 1, 2, 3, 4, like that. So I think I've rather ruined my drawing by doing that. But okay, I'm not going to stop the video, but I'm going to try that again. And so you can imagine doing it. There we go. Up here, maybe a little taller this time. And there's my tetrahedral. Okay, so zip, 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 up. But you don't have to draw it that way, thankfully. This will suffice. In fact, this is very good. And my electron group geometry is tetrahedral. Again, since I have no lone pairs, my electron groups are also arranged in the same way as my whole molecule is. So my molecular geometry is also tetrahedral. Great. Now, last thing, the bond angles. Each of these bond angles, each of them, are identical at 109.5. And they will be identical if each of these atoms are the same. So the perfect tetrahedral angle is 109.5. Now, what if I have 4, but only 3 are bonding, and 1 is a lone pair? We'll do that. And then after that, we'll do 4 total, 2 bonding, 2 lone pair, and that'll be it for the 4. I'm going to pick up the pace a little bit here. I hope you're getting a rhythm to this, and it's becoming a little more intuitive. So here's my 4 total. This time I will make 3 of them bonding, 1 non-bonding. So my central atom has AX3E1. So a Lewis structure might look something like a lone pair, and then okay, so that would be my Lewis structure. What is the geometry? So when I have 4, I like to put my central atom in a circle here. I don't have to, but even though this is non-bonding or a lone pair and these are bonding, I treat them all equally in terms of their repulsion. So how do I arrange these 4 pairs to minimize these repulsions? I'm going to place the lone pair first. Because all the positions initially are equivalent, I'm just going to put it up there where I don't forget about it. And my lone pair, I put that little hood, electron hood on it. And I saw before that if that were bonding, it would be a stick, it would be a bond. But I had one pointing on the top, which is now being taken by a lone pair, and the other one went like so, and then to the back, or maybe the front, depending on how your eyes are interpreting this 3D rendering. And so you have it. So the electron group geometry here is, again, it's really determined by this, isn't it? Let's recap for a second. When I had a total 2, it was linear. When I had a total 3, it was trigonal planar. And when I have a total 4, the electron group geometry with 4 is always tetrahedral. But this time, one of these electron groups is non-bonding, so that as a molecule, the molecular geometry is, since I don't have a post here, I just have 3 bonds here, this is called it's a trigonal pyramid. So it's like my tetrahedral without the tall part of it up here. And so it's a trigonal pyramid, or if you like, trigonal pyramidal geometry, but that's just too many adjectives, so I'm going to call it a trigonal pyramid, and that's it. And don't draw a bond angle between a lone pair central and an atom, because bond angles must be between atom bonds, so it must be atom, central, atom. And this one, bond angle is the same as this one, and it is about 109.5. It's probably a little bit less. It's compressed a wee bit because of the bulkiness of the lone pair, so I just say about. But when all of your substituents are the same, you can say 109, and they wouldn't be here because I have a lone pair. Okay, so electron group geometry tetrahedral, but the molecular geometry is trigonal pyramid. All right, last one in the group of 4 would have, again, a total of 4, but this time 2 bonding, 2 non-bonding, A, X, 2, E2. We're picking up the pace. The Lewis structure will look like lone pair, bond, bond, lone pair. Okay, now no geometry there. How do I determine the geometry? Well, it's central atom, and I have 4 pairs. And the way that I arrange 4 pairs is tetrahedral. I'm not drawing it in yet because before I make these 4 bonds, I realize, oh wait, now 2 of those are lone pairs. So I can choose any one of these initially equivalent 4 positions. So I'm going to choose the top for my lone pair. And remember, I had a stick this way, and this way. So I'm going to put another lone pair here, and I'm going to put my bond here and my bond there. X, X. So my electron group geometry is determined as soon as I know that it's 4. If I have 4 total, the electron groups are still arranged. You can see the tetrahedral nature to the groups. But my molecular geometry, because 2 of those are lone pairs, and they don't have atoms sitting there, so my molecular geometry is different. And it is instead V-shaped or bent. And again, this is about 109.5, but I think we're very safe to say that it's less than 109.5. And that's because I don't just have 1 lone pair pushing down on it, but 2. So I think it's probably muscling those two bonds a little closer together. So I would go with a little bit less than 109.5 for that. Okay, and it is bent. You'll also see V-shaped, but we'll take bent. So you're probably wondering, do I have the case where I have 4 but just 1 bond and 3 lone pairs? No. So that's it. We're moving now to 5, and we only have to go to 6. So hang in there. We're doing really great. This is a really, really good review for the exam. It's a very important part of your evaluation in this course. I know that the timing is at the end of this, and it's not ideal, but you did do it in the lab, and so hopefully there's some physical memory that you can help learn this with as well. So I've moved now to 5 total number of pairs, and our first consideration is to make them all bonding and none of them lone, and that gives me AX5 or AX5E0, just to make a point of there being no lone pairs. So I would have a Lewis structure that looks something like, sorry, it's supposed to be somewhere else at this moment, maybe, just checking. So I have a central atom and then 5, so it might look something like 1, 2, 3, 4, 5, something like that, our Lewis structure. And it told us nothing about the geometry. So I have A. And I'm wondering, how do I arrange 5 electron pairs around a central atom so that they minimize their mutual repulsion? Well, the 5 makes use of a plane and the space above and below it. And so there's a flat triangle kind of coming out of the paper here. So we have the x's like this, and then there's an x pointing up and an x pointing down. It might be, I don't know, you might like to do this better. To draw this open triangle like this, don't make it equilateral because although it is, you lose the 3D perspective if you do. And then imagine a central spot there, but a bond above and below, just like that. And then place your central atom right in the middle like so. And you have an X above and below. And you see that triangle? We're just showing you the cage of the plane. And those lines in red were not actually bond lines. And I have X, X, X. So hopefully you can see that this part is a plane. In fact, it's a trigonal plane. And then we have these top and bottom positions that are out of the plane. So for this molecule, we would have an electron group geometry equal to, and let me just do something to the structure to really make this, hopefully make it stand out. I'll just use a pen. Or actually, no, I'll use the red because, okay, I'm really changing my mind here. I'll stick with this. If I join like so, like so, like so, zip, zip, and zip, it's getting very cluttered and messy, but you might be able to see that I have a trigonal pyramid on top and a trigonal pyramid on the bottom. And in fact, the electron group geometry is a trigonal. It's not a trigonal pyramid, it's a trigonal bi-pyramid because there's one on this side and on this side of this plane. That's the electron group geometry. The molecular geometry, yeah, you guessed it, it's the same because all these positions, none of them have a lone pair. So the molecular geometry, the shape of the molecule, is also trigonal bi-pyramid. All right. Next, we are going to just spin this around to get the clean sheet. And I'm going to work with 5 total, but I'm going to have 1 lone pair, so that makes 4 bonding. So I have AX4E1. So the Lewis structure would present something like this. And as soon as I have 5, I know that I have that basic structure of the trigonal bipyramid electron group geometry. But one of the positions is going to be taken up by a lone pair. I think that worked, what we drew the last time. So let's try and get that plane again. I have a position here, here, and here. And a position here and here. So the question is, which one of these 1, 2, 3, 4, 5 positions is a bit roomier for the lone pair, which needs more room than a bonding pair? These 3 positions on the plane are equal, but these 2 are different. And it may look like they have more room, but they actually have less room because they are 90 degrees to their nearest neighbors. Of course, 180 here, but they have 3 90-degree neighbors. And this top one has 1, 2, 3 90-degree neighbors, whereas this position only has 2 90-degree neighbors and 2 120-degree neighbors. And so I am going to use the magic of whiteout and put a lone pair in there instead. And then I'll fill in with my 4 x's. So what kind of shape is this? Well, first of all, the electron group is still arranged, because I have 5 total. The electron group geometry is still arranged as a trigonal pyramid. But my molecular geometry, since I don't have an atom here, is not trigonal pyramid. My molecular geometry is what? Well, you might not see it right away. This is sort of a bent thing here and then 180 here. But watch, if I just do this for a second, do you see how this is sitting like that, and then I have something flat? So it's actually called a sawhorse. It's the shape of a sawhorse. So let's put that back and give it a name. There you go. What are the bond angles? Right. The bond angle right through here is 180. This bond angle is 90. I have another 90 there and another 90 there, but 1 is good enough to show. But in the plane, this bond angle is 120, so there's a lot going on in these total 5 electron pair groups. So electron group geometry, molecular geometry. All right, next one, 5, 3, 2. Let's do it. Really hope you're doing these with us on your own, playing the video, not rushing through it. I know it's not the most stimulating one-way conversation, but yeah, I hope it's helping. So 5 total, and let's make 3 and 2, and so that's A, X, 3, 2 lone pairs. So the Lewis structure that I would have drawn would have, 2 lone pairs and 3 bonding pairs, like that. What's the geometry? Well, again, I'm looking at 5, and I know that when I have 5, I have the 1, 2, 3, 4, 5. And I'm not drawing them all out yet, because I know that 2 are lone pairs. And remember, we said that the positions with more room are on the trigonal plane here. And so make sure that you place your lone pairs first and put them in the positions on the flat part before you add the rest of the molecule. X, X, and X. So this one's kind of neat, because my electron group geometry is, of course, still, because it's 5, there we go, is still a unit, right? Trigonal pyramid. Sorry, pyramid. There we go. Computer keeps going to sleep, so let me just wake that up. There we go. Make sure everything is in view. Right. So my 5 electron pairs are arranged in a trigonal pyramid, but I only have 3 bonding pairs, and I hope you can see that this is actually, let's switch colors again. I have a right angle here, I have a right angle here, and I have 180 there. So those are the 2 angles at play there, and overall, my molecular geometry, I don't know if you've looked up these names, but it says for this configuration, this molecular geometry is called a T-shape. And it really is. It's a T-shaped or T-shape geometry, because that's straight, right angle, so it's a T on its side. Okay, let's spin this around. My last one for 5 electron groups is to do 5, but to have 2 bonding pairs and 3 lone pairs. 5, 2, 3 lone pairs. So this is AX2E3. So that Lewis structure would look something like that. Kind of strange. But I know it's a base geometry, an electron group geometry that has 5 pairs. So an electron group geometry of a trigonal bipyramid. And again, before I write these positions with lines, which would imply bond pairs, I want to see, in this case, all my lone pairs are going here, and I don't have any positions left. I only have the top and bottom ones. So my X goes here. I forgot to draw them in on this side. So you see that? So my electron group geometry, again, is trigonal bipyramid, because 5 are arranged still in a trigonal bipyramid fashion, but my molecular geometry is certainly not a bipyramid. My molecular geometry is, look, what's left? Everything's lone pairs except for this. So it's actually just one bond angle of 180. The molecular geometry, in fact, is linear. So one thing you'll want to be able to determine when you've drawn a correct structure is whether the molecule is polar or not. And it's interesting here, it's actually quite symmetric, that there's equal pull of electron density this way. I shouldn't say pull, but the lone pairs are directing themselves here to even that out. And these atoms X are just opposite each other. And so this would not be a polar molecule because the electrons are pointing, it's all balanced. It's very symmetrical. That's it for 5. We are now moving on to 6, and that's our last geometry consideration, our last total electron groups on central atom 1 to consider. Okay, let me fix this. Okay. 6, last one. Let's do AX6E0. So all bonding, no lone pairs. And, something like SF6, the Lewis structure, would look like A and then 1, 2, 3, 4, 5, 6. What kind of geometry does this molecule have in 3-dimensional space? Well, what can we do? So we're past 5, so I'm not going to draw that trigonal plane, but I have 6, and the way that I draw 6 is I actually draw a parallelogram first. Okay, I think we can all do that. So it's actually a square, but coming out of the plane of the paper, and I have a position pointing up and a position pointing down, and then fill it in. The A is central, and all of the positions are occupied here with atoms. In other words, all of the 6 are bond pairs. So see how the plane is not the bond, it's the corners that are, the pointing to the corners are 1, 2, 3, 4, 5, 6. And as a structure, the electron geometry is actually called octahedral, because this is really like a diamond here, an octahedral. It's a tetrahedral on top and on the bottom, so it's kind of like a bi-tetrahedral, if you like. And we don't call it that, we call it octa because it has 8 sides. So don't do what I just did, filling in all those sides. I just wanted to show you why it's called an octahedral. So the electron group, whenever you have 6 electron groups, the electron group geometry is octahedral. And because all of the positions are occupied and none have lone pairs, my molecular geometry is also called octahedral. octahedral. Okay, so likely question is, what if I have one lone pair? Let's try it out. One lone pair. So 6 total, 5 bonding, 1 lone pair. That will be AX5E1. So I have a central atom with 1 lone pair, and then 1, 2, 3, 4, 5. So weird looking Lewis structure. Let's make it into a real molecule with some geometry. So whenever I have 6, my signal is, the 6 signals me to draw my little parallelogram with a top and a bottom like that. And then I fill it in A central. And now I have to place the lone pair first. And if you recall, when I had 5, I realized that the positions in the plane had more room than the ones above and below. The thing about an octahedral is that each of these positions are actually identical. And so you can put the lone pair wherever you like. I like to actually put it right here on the top. And then I can see very quickly then that the name of this geometry that results, the molecular geometry, is going to be some sort of pyramid, but we're not there yet, because the first thing I want to do is name the electron group geometry. And I think you've caught on that the electron group geometry is always related to the total number of groups, regardless of their distribution. So because I have 6, total, they are arranged in an octahedral fashion. So my electron group geometry is octahedral, but I have 1 lone pair, so the molecule itself is not octahedral, but in fact it is a square pyramid. You see that? It's kind of upside down at the moment. If I had put my lone pair down here, it may have been more obvious, and that's up to you. You could do that. But in any case, the correct molecular geometry, when I have 651 like this, or AX5E1, is a square pyramid. We are almost done. We have 1 left. 1 left. Okay, let's put total 6, but 2 lone pairs, and so 4 bonding. Last one. I think it's the last one. Okay. Oh, there we go. 6 total. I want to make 2 of them lone pairs, so I have 4. And that is AX4E2. My Lewis structure looks something like maybe that. Kind of exaggerating the nonsense of the Lewis structure, because, I mean, it's not nonsense, it's just that it really doesn't tell you what the bond angles are. Actually, I should pull the other one back. I will in a moment when we're done this one, and just make note of the bond angles that were on the last one. Okay, so I have 6, so I know, oh yeah, when I have 6, I'm starting out with an octahedral electron group geometry, so I have to do my square plane in the middle and my position above and below. I put in my central atom, and I go 1, 2, 3, 4 out to the corners, 5, and 6. Oh shoot. So 2 of these were lone pairs, and because each of these are identical, I really want to make it easy for myself. Okay. After talking this long, I am not going to start over or delete that. So I'm using whiteout. I'm not getting that. And I'll have to get that later. And I have a lone pair here. Okay? Remember, I'm not drawing a bond to a lone pair. I'm sorry about the phone. I'm in my office. So 1, 2, 3, 4. So the electron group geometry here is, it's 6, And these pairs are arranged, whether they're lone pairs or bonding pairs, in an octahedral electron group geometry. However, the molecule itself is not an octahedral because two of those positions are occupied by lone pairs. The molecule itself is planar. In fact, the molecular geometry is called square planar. A nice easy name that tells you exactly what it is. So what are the bond angles? Don't put a bond angle from a pair to a pair. It has to be atom, central atom. So all the bond angles here are 90. They're all 90. Okay, and let me just pull that other one back where we had the square pyramid. And they were all 90 as well. And before that we had the octahedral. And on an octahedral, everything is also 90. Yeah, they're high energy things. So I'm going backwards now, and you can go back among your notes. And where we had the bipyramid, we did those bond angles. We did that bond angle. And we did those bond angles. And this one, 120, 120, 120, but then right angles from above and below. Then we did all the other bond angles. So we're done, folks. You are ready to handle any Lewis structure and do geometry on it. And I think what we're going to do for the exam is have a list, but in no particular order, of these names. So don't waste your time memorizing them. You'll be able to choose from a list. Trigonal pyramid, octahedral, T-shaped sawhorse, etc., etc. Okay? All right, let's cut this.